I wanted to work through a problem that involves Lenz's law, which describes the direction or the orientation or the sense of the induced currents, induced EMFs in electrical circuits. This problem also involves using the right-hand rule for the magnetic fields that created by currents in loops of wire or solenoids. And it also involves using the right-hand rule both to calculate the sense or the direction of the magnetic field from the current, and also to infer the direction of the current for a given sense or direction of magnetic field. Okay, so in this particular problem, we've got two circuits. There's one over here on the left and one over here on the right. The one on the left involves a coil of wire or solenoid. The one on the right also is a coil of wire or solenoid. The one on the left, the solenoid is connected through a switch to a battery so that we can energize or de-energize the solenoid with the battery and the switch. The one on the right is just connected to a resistor. And in this resistor, we'll see an induced current when there is a induced current induced due to a time-varying magnetic field or a time-varying magnetic flux through this right-hand coil. So the question says, find the direction of the induced current in the resistor in the right-hand circuit when the switch on the left-hand circuit is closed. That's when you energize the solenoid on the left. And then secondly, when the switch on the left-hand circuit is opened, that's when you would de-energize the left-hand side solenoid. At other times, when the switch is simply just sitting there open, there's no induced currents or EMFs in the right-hand circuit, or the switch is just sitting there closed. There's no induced currents, no induced EMFs in the right-hand circuit. The only time or moment or instant that there is a current in the induced current in the right-hand circuit, induced EMF in the right-hand circuit, is that instant, that moment you shut the switch, or that instant moment you open the switch. So let's imagine we close this switch. When we close the switch, we're going to make a magnetic field from this solenoid. And that magnetic field from that solenoid or that curl of wire, the direction of that magnetic field you can get from a right-hand rule. So it's the right-hand rule that contains two directions in it. It's a right-hand rule that contains the orientation of the current, direction of the current. That's going to be represented by my fingers. And it's a right-hand rule that contains the direction of the resulting magnetic field. That's represented by my thumb. So you curl your fingers in the direction of the flow of electrical current, and your thumb will point in the direction of the resulting magnetic field that's produced from this loop of wire or solenoid. So let's do that. Firstly, let's recognize that the battery down here, positive terminals on the right, negative terminals on the left, the current will flow from the positive terminal around the circuit through the switch to the negative terminal. So it's flowing upwards on the right-hand side of the left-hand circuit, and then it will flow downwards on the left-hand side of the circuit. So if we think about how the current's orientated on the solenoid, it's coming out of the screen at the top. I'll put a bunch of dots up here to indicate that. And it's going into the screen at the bottom of the solenoid. I put a bunch of crosses down here. And I'm going to curl my fingers of my right hand such that they come out of the screen at the top and they go into the screen at the bottom below the solenoid, and my thumb is pointing towards the right. It's telling me that the magnetic field lines created by this configuration, created by the solenoid, travel from the left towards the right. So this is the magnetic field that we're making with this solenoid when we switch it on. So that's the magnetic field created by the solenoid when the solenoid is energized. Now let's turn to the induced magnetic field that's seen in the, or created by the right-hand circuit. And that's given by Lenz's law. So when we switch on the left-hand circuit, suddenly there's a magnetic field that is flowing from the left to the right in the neighborhood of this right-hand circuit. The right-hand circuit's going to want to counteract that change, cancel out that change by inducing its own magnetic field. So the first thing I do to figure out the direction of the induced current in the circuit on the right is actually think about the direction of the induced magnetic field in the circuit on the right. It's going to be the opposite to the change that's just happened. So this magnetic field, because we just made from the left-hand circuit a field that goes towards the right-hand circuit's going to try and counteract it with a field, induced field, that's towards the left. So in magenta here is the induced magnetic field. Let me call that the induced. Over here on the right in green, that was the original magnetic field created by closing the switch. So now we've got the induced magnetic field. When we turn the switch on, we can figure out the direction of current that must be flowing in the circuit to create that magnetic field. Again, it's this right-hand rule for a coil or a solenoid that relates the direction of the current, represented by your fingers, to the direction of the field, represented by your thumb. This time we know the direction of the field. So we know the field is going towards the left-hand side. And then we just look at the way our fingers are curling. My fingers curl in at the top of the solenoid. So I'll put crosses upstairs here to indicate the current's flowing in here. And they curl out at the bottom of the solenoid. So I'll put dots here to indicate the current is coming out of the screen downstairs here. So the current comes out on the right-hand side of the solenoid, flows from right to left through the resistor, and then it flows back up on the left-hand side of this circuit into the solenoid. And so that's the direction of the current when we've closed the switch in the circuit on the left. Let me just denote that. So the answer to 1 is induced current. Okay, so now we'll just let the solenoid sit there for a while. The solenoid on the left is energized, it's creating a magnetic field. But because that magnetic field is not changing, there's no induced current in the loop of wire of the solenoid on the right-hand side. And then we're going to open the switch. What happens when we open the switch? Well, what happens is that this magnetic field, the one in green, the one from the energized solenoid, that's going to disappear. That's going to go away. That means that the circuit on the right, that sees a magnetic field that was towards the right disappear. It's going to want to oppose that change. It's want to counteract that change. That's Lenz's law. And so in the second case, when we open the switch, the circuit on the right is at that moment also going to create a magnetic field, but it's going to be a magnetic field in the opposite orientation. So it's going to be a magnetic field where the field lines, there's a couple of field lines, head from the left to the right. They're replacing the left to right magnetic field that has just disappeared because we open the switch. So this is the configuration of the induced magnetic field when we open the switch in the right-hand circuit. So what direction of current does this correspond to? Again, that's a matter of that right-hand rule for a coil or a solenoid that relates the direction of the magnetic field represented by the thumb to the direction of the current represented by the fingers. So in this case, we know the magnetic field is now towards the right. So I point my thumb towards the right, and my fingers naturally curl with them coming out of the screen above the solenoid. So the currents are flowing out of the screen on these wires, and then they're flowing, my fingers curl in, the current flows in below the solenoid. So I put crosses down here. So in this case, it means that the current is now flowing down this wire on the left-hand side. It will flow left to right through the resistor, and then back up to the solenoid on the right-hand side. That's now the direction of the current. So let me write that down. In answer to what's the induced current when we open the switch, that induced current is now flowing in the opposite direction than when we close the switch. It's going through the resistor from the left to the right. Anyway, that was an example of working with Lenz's law. Working with time-varying magnetic fields, we switched on the solenoid, we switched off the solenoid. Those switching on and off for the solenoid created the induced currents, created the induced EMFs because there was a changing flux. And then we worked with Lenz's law and the right-hand rule to find the direction of the currents in the right-hand circuit for the cases of switching on and off, energizing, de-energizing the left-hand circuit.